Test 1, 2. Test. Ça marche?
Oui, ça marche. Des fois, il faut faire attention si tu parles. Oui. Tu parles en fait en direction du micro. Parce que des fois, il y a les gens qui ici mettent ici, on parle vers là, on n'entend rien. Et puis, seconde chose, s'il y a des questions, c'est toujours bien de la répéter.
Oui,
il y a souvent c'est oublié. Mais...
Oui, je vais essayer.
Et puis le reste, normalement, c'est pas très important. J'en ai marché, donc on va voir si la vidéo est bien.
Allez, comme ça, comme ça, comme ça. C'est bon, on bouge plus. Zoiets?
Parce que c'est vrai, il ne marche pas très bien, ça fait...
D'accord.
Bon, okay, then we're going to move on to our next talk today. Kees is going to talk about running MINIX on ARM. And without further ado, let's Kees explain everything.
Hi, thank you for coming and being here. A few years ago, Andy Tanbaum was here at Keynote. Who was there at that time? 2 or 3, a few people there. And well, I just watched that keynote and I thought that might be interesting. And later on, there was a little sign note on the jobs posting saying searching for a programmer for the MINIX team. First year I didn't respond because I was busy with other kernel and Android related development. But like 1.5 years ago, I decided to try it. So hence, that's why I'm giving this talk right now, because I applied for that job. I got it. This talk is about MINIX on ARM, and also a bit about the history of MINIX, because I need to put it a bit into context. If you have questions, just go ahead, because at the end everybody talks and it just doesn't really ever work. Right, what you see in front is a box running ARM that says MINIX on top. Some guy in China decided that he had to make hardware called MINIX and put it on the box. This is not our stuff, but would be nice to run MINIX on it. Right, if you get bored during the speech or the talk, go to MINIX on ARM, the wiki, try and download MINIX, build it, and you might learn something. Right. Halfway the 80s, Unix already existed for quite a while, but the Unix war started and there was quite a debate about which sources were permissible to use. At that time, Andy Tanbaum said, I want to create an operating system that can be used to teach, so everybody should be able to read it. So he created MINIX, Mini Unix, in 1987 with a book, Operating System Designs and Implementation. And that went quite well, that book. Also a Usenet group was created, compos.minix, that is still, I think, known, I hope, by most of you. Well, that was the 80s. In the 90s, 91, so 3 years later only, Linus announces on the MINIX news group that he's doing an operating system, nothing big or serious like GNU. Well, who knows. 1992 only, 386 BSD gets released, and that's also because of this Unix wars. It was only at that time that it was clear which sources were permissible and what needed to be replaced. So if you put it into context, you really see that MINIX and Linux 3-4 years difference, and we're talking now about 25-30 years ago. So that's quite an interesting start that they both had around the same time. MINIX, however, always remained a tool for educational purposes, but also with vision. The vision was to be able to teach OS and just keep it simple. And that's why also many people wanted to add functionality to MINIX, but that didn't happen because it would not be suitable for the book anymore, because you could not read the code because it would become too complex. Right, so back to the zeros, the year 2000. Around 2005, the focus of MINIX changed dramatically. The idea was to make it now the target was to make it usable on resource-limited computers and focus on reliability. At the same time, also the code was released under BSD licensed. So we can say that starting from 2005, something different happened. It was still called MINIX, the same people were working on it, but it was, the purpose changed totally. At that time, research started to be doing on reliable computers. How could we create operating systems that would recover from fatal errors? And think of it like this: if you have a browser and your web page doesn't load, you will not nervously restart your browser. You press F5 a few times. It might work with YouTube or whatever. If your browser crashes, you will not restart your X session, you will just restart your browser. And that same analogy can apply to drivers. If your driver crashes, why would a restart of a driver not be enough? Why do I have to crash my computer? So that was a bit the vision, I think. And then 2008 came, and European Research Council is an institute that donates money to do research for the good, I think. And a grant was awarded from €2.5 million euros to do research on really reliable and secure system software. And from there on, a lot of more development of what I'm going to talk to you now is applies from that era, I would say. So if we look back, starting 2005, a lot of things changed. The goal of MINIX changed, and also the licensing, and that made a difference. When I joined, MINIX 3.2.0 was just released. That's in 2012, February 2012. And it contained a few interesting features, I think, right now. Clang was a default compiler, which I think doesn't happen yet on Linux, for example. But all the features that were implemented in the past during the research are now part of the operating system. So MINIX could recover from crashing stateless drivers. So many drivers in the system can be separated into drivers that will have a state and those without. Those who don't have a state are quite easy to recover from. You just reinitialize the hardware and you'll be able to continue. Some drivers will be harder because can you hear me? Is there? Sorry. So some drivers will be harder to restart because they contain states. So the research also went in that area. What can we do to recover those drivers? And that's basically what happened, is that you could split the code and the data. That means that you can restart your driver and get your data back again. Another area of research is live updates, where you have a driver, you might know there's a fault in it, and you would like to restart it. You would like to replace it with newer version of the same driver. Then you also need to take over that state information. And a lot of that work actually is based on Clang, because you can instrument your code and know what variables are and do things like that. That live update is not part of 3.2.0. Also, a lot of changes were integrated. So no longer it was a small self-written library C, no longer it was LS self-written, but more and more code was imported from NetBSD. The switch to the alpha format. So I think 2012, when I joined, was already a MINIX that was not like we know it or knew it, I guess. So what does it look like currently? Basically, there's a kernel process, one single process that will run in the supervised mode and will do really the bare minimum possible, which is IPC, so inter-process calling, low-level interrupts, context switching, timers, a little bit of startup, but that's it. And most of the other features are implemented as normal user processes, just above which you see. And are separate processes. Even things like virtual memory management is extracted from the kernel, and that poses some interesting challenges, but that's what happened. Process management happens there, and drivers also are just normal processes that can do IPC to the kernel. Above that, there's still the NetBSD libc and the novel POSIX tools you'll find. So, from a user's perspective, you should not notice too much. It's MINIX below, but right. I hope that's clear. So also on startup, you will get like 12 processes, one kernel that gets loaded, and 12 modules, and it will need to do some starting of all those processes before the init can be called. Features, reliability, the driver restart I already mentioned. Ease of code development, because you have those small drivers, it's quite easy to fiddle around with a single driver, copy a file and just start it, try it, remove it, a bit like kernel modules, but a bit more flexible, I would say. And a very interesting feature is it's a single build system. It's self-contained, so you do a git, if you follow the guide I just posted, you'll see that you just do a git clone of code, and it will, you call a build script that will build your cross compiler, it will build all your host tools, and the end will be an image that you can flash. So we made some choices there. Right, now to ARM, I think we need that. Why MINIX on ARM? Well, the second point said already, like, MINIX didn't make it until to the desktop. It just didn't happen. Linux barely did it. So on ARM, a lot of more chances are to be made for a smaller operating system. Also, embedded hardware could make good use of the features that MINIX has, the driver restartability and things. So in the end, it's an effort to make it more appealing to people. Yeah. The target we choose for this is a BeagleBoard XM, which is a board from Texas Instruments that released like 5-6 years ago. They did their first release of that board. It contains a OMAP 3 system on chip. It's a Cortex A8 ARMv7 system with 512 megabytes of RAM. It was a nice system to target because the documentation is good, open. There's a good community around it. And there was an emulator for it also. There's a QEMU emulator to emulate that target, which is very nice if you develop low-level code to be able to grab that stuff. So pointing to ARM from where we were, from an OS perspective, what does it mean? So we have different color codings here. The blue things are things that needed to be modified because the kernel is a single thing. So low-level interrupts, of course, context switching, that code, the low-level assembly code was to be changed. Overall, above the libc and a lot of things were just unmodified. It's all C code, and so there's a lot of code that was not modified. The things you see modified, blue also above is the virtual memory manager. I'll discuss later, and just driver work, which all are things that you need to do anyway. But overall, the changes were not that bad for that part of the system. So what you do, you go assembly programming, you do your interrupt handlers and all that stuff. It's very interesting, but reality is a bit different, I'm afraid. You have to do a lot of things before you'll get to a working operating system that's been ported. Of course, cost calculation, which might sound like trivial, but if you come from a system that really was designed to be able to build on the same system and run on the same system, all of a sudden you can no longer use system headers. There's a lot of things that happen that you'll just have to cope with. Stolen from NetBSD. Build system, same story, mostly stolen from NetBSD, how they do their stuff. And that also included importing headers for different data types. The kernel and VM I'll discuss later, and driver development. I'll discuss that already. Right. MINIX kernel already discussed actually, I think. Yeah. So what's interesting to say, if you look at the specific part, ARM specific part of the kernel, it's about 3,000 lines of C code and like 700 lines of assembly code. So that's a bit amount of code that needed to be added, and that includes the OMAP specific things like timers and things like that. So that's quite small actually. I think it's like a normal driver for some piece of hardware. Yeah. More interestingly, because of its history, MINIX did not use page tables at all before 3.2.0. It uses something called segments, Intel segments, which they work differently, which I actually don't know exactly how they work. So a big part of the work to get it working on ARM was implementing page tables, implementing that both for Intel and for ARM. So map regions is more that we map ELF sections to page tables, so we can do that. Most of the time I spent anyway was debugging caching issues on ARM, because it's complicated, and it's really complicated above what you expect. So where I came from, I did kernel development, I did Android development, but some areas you just don't touch. It works already, or you call the vendor, I don't know. So it was very interesting to work in that area, but it was also quite a reality. Like it's not that easy. MINIX, because it has all those different processes, there's a lot of context switching. Because if you call want to do a simple system call, get time or something, it will, well, get time is not a good example, but another system call, it will call the kernel and then really do a context switch to the whatever process is in charge of implementing that system call, and switch back. So a simple system call can cause two context switches to happen. While on Linux it will only do one, because it will only go to supervised mode and go back. So we need to do some more work on improving that. It's both challenging, but on the other side also there's so much work to be done on just getting the system to build, work properly, and have a reproducible result that we didn't get to that yet. Help is welcome, by the way. The driver model of MINIX is interesting, I would say. It matches very well what you do when you do bare bones programming. You will read out stuff, you will wait for your interrupt, and you will continue your stuff. You will not have to take into account that you're in a kernel, that you cannot halt the system. You're just doing one thing, and the rest of the system, it doesn't impact that. And that matches pretty well with what the MINIX drivers do, because they are just normal processes. So they are allowed to sleep, they are allowed to do most things that you expect from a normal C program. So really the model went from making sure you understand the hardware, using whatever tools we had, debugger or Code Composer Studio, towards the implementation on MINIX was very straightforward. Interestingly enough, also the driver model is really that, like, if you have three buses on your controller, on your hardware, MINIX will start 3 processes that just manage one of those buses, and that simplifies the code because you don't have to look back at anywhere. So that's one thing it does. So really typical driver, once it has been made to work bare bones, is really we'll do a main loop, handle a request, ask work from the kernel, and wait for an interrupt. Really just in somewhere deep in your code, it will do like wait for interrupt And when that happens, it will continue flow. You don't need to return the flow to the main process because nobody else is going to call you at the same time. Of course, there were some missing bus drivers, like I2C was unknown to MINIX, and so we had to add that. No questions so far? Right. So about a year later, we finally got it all working. MINIX 3.2.1 was released. It had like stealth mode ARM support, meaning that the code was in there, but we didn't officially release it. We didn't felt it was the right time. But it contained support for Bigword XM, serial MC driver, frame buffer, GPIO, and a few more of those things. And well, we're offered to discover the world or to let the world discover us because it's been really in an attic for quite a while, and all of a sudden you've got something that's you've been working on and you want to make something out of it. The first idea was like let's put MINIX into space, or let's do something like that. That's a symbolic thing. Now it's only the world, so no universe but just the world. And to do that, we went to Embedded World. Have you ever been there? In Germany, one person, two, a few there. Right. The sales pitch was, well, we're a BSD licensed operating system, so not GPL, so you can just take it and do whatever you want with it. Small, we had those features of reliability, and the best of both worlds approach, where we said, well, you've got a whole POSIX user land, and but the kernel is not monolithic, so you have the ease of development. And we pitched that. We just talked to people like, what do you think of this? Right. So now I'm going to show a movie of us at this embedded world.
Hi, I'm Andy Fandom, and here at Embedded World 2013 in Nuremberg. I'm giving a demonstration of MINIX 3, fault-tolerant operating system. MINIX is running on the single board on the Cortex-A8 processor line. Now I can artificially inject faults with the frame buffer driver running this display by pushing smile. So I'm going to press the button. Here on the screen, you can see the faults were injected. The result was a crash of the driver, and then it's detected the crash, automatically repaired the system by starting the driver again and continues to run correctly. And so this ability to continue working even in the presence of software faults can be useful for other applications that need high availability, such as pacemakers, hermetic devices, industrial automation systems, power plants, and so on. The MINIX is a system that can survive software errors in its own operating system software, repair them automatically, continue to run something that's available in high availability applications.
So that was really fun to be there with Andy Tannenbaum, and people really interested in meeting him also, and things like that. We also had a sign saying crash our driver, pick an egg, and people would be able to crash our drivers. They could pick an egg, but also the driver would restart. I've got the same demo here actually running. It's doing the same thing, so if you want later you can press it, or I can see if I can switch. Yeah? No. Let me just continue like that. I might continue the demo later. So what did we discover at Embedded World? We were actually, I thought I knew what embedded development. Yes, sorry?
You mentioned about injecting errors in your driver. What are we talking about? Hardware errors? What kind of code can you inject in your driver?
Right. So I'll still go to the demo then. So this is the demo. This is, if I press on the button, it will start counting here. Stop it, and it's going to inject faults. So what kind of faults can we see? keyboard errors, which doesn't apply. Right, well, I'm just going to see, you see a few of those things here. It says like, it will randomly stop the process and increase the program counter, which is quite nasty, I would say. It inserts some different areas in the memory. It replaces some instructions with knobs, and actually here what you see is really the frame buffer driver, which is a driver that's running here, that's displaying, really gets a page fault to cope with, and crashes. After that, it just restarts itself immediately. Restarting is not per se always the best thing to do. Sometimes you will just take, well, if it's a train that is driving and some error occurs, you might just want to stop at all. Could be. But sometimes you want to restart. It's just detecting that there's an error is already quite an achievement somehow. So that kind of errors. Does that answer your question? Kind of. Yes?
One question concerning the demo. The lamp is blinking quite irregular.
Yes.
A reason for that?
It's a reason, yes, because we didn't touch the demo since the embedded world, and it just this is a demo. And the same thing. The screen, you will see that sometimes it goes faster, it goes slower. It's not really a problem of the port itself. It's not fast. That's one thing that's could improve, I would say, because if you compare the x86 MINIX to Linux or something, it is slower, but it's not unbearable. And here there's still work to do to make it faster, and it's mainly the context switching that needs to be improved. Right, let's try to restart the presentation. Right, so we went to Embedded World, and we expected like the competition. What's the competition of MINIX? I don't know. I would say Linux, because that's all I've seen so far. It was not at all like that. If you go to Embedded World, you discover that many people you talk to don't know Linux. So who you're talking to people who are used to developing for very small devices, doing hard real time, and they're either open source or ask a lot of money, for what they do. From free to very expensive. Many just run a microcontroller. Some will be able to run multiple threads of a single process, but still will not do proper detection of error, or it will all run in a single address space. And then there's the entry of Linux in that market. It's still not a good sell, I think, because it hasn't got that feature that you can certify how long it's going to take to do something. So it's hard to sell MINIX, but also Linux was hard to sell actually in that area. People want either a very simple microcontroller, that was our conclusion, without the external memory, without those features, because it's easy, it's cost down, you can prove it works. And the higher you go in the full chain, the harder it gets. Interestingly, if you go higher, you start to go into using other hardware, FPGAs, or using virtualization, right? Again, it gets possible to run a full OS, but do the real-time part on a different core or a different part of the hardware. So that's what we discovered there. So we didn't have much clients after that embedded world. Still, it was quite awesome to be there and to learn about all that stuff. So after that, last year or something, that was a year ago, we're currently just working just on reliability features are already part of MINIX. So what are we working on right now? We're just trying to integrate as much code as possible from NetBSD and get this base port working. We ported to the BeagleBone black and white. know them or not. Those are quite nice boards, especially the Big Bone White is a very nice development board. And we try to increase community involvement. And that means that externalizing mailing lists, we have a Jenkins setup, Garrett setup, so we can do open code review. We got our first external committer, official committer there. Thomas Cote, who did also Google Summer of Code with us on porting to the ARM. So that's the kind of things that we're currently targeting. I mentioned already, like, currently it's still self-contained system. You just clone it, you run the tool, and what outputs is really a single binary that will work on the different boards. That's the current status of it. For the bigger board, we support NMC, the frame buffer, GPIO, power management, a few more things. More completely is listed on the website, but we're mainly focusing currently on the bigger bone black. With a bigger board already, you could create an opening system doing something useful. We've got GPIO, we can access a screen. You can already create small embedded devices without too much hassle. And it's a bit of a difference from Linux, because you would be tempted to write a driver quite soon, actually, because it's easy. We're currently continuing work to integrate. That means more NetBSD type alignment, so we have all kinds of 16 bits timers or other things that we removed in favor of 32 bits or 64 bits values, and that causes quite some headaches. So that's the work we're currently working on. More clone goodness, memory map is implemented, and we're moving towards a more open organization. What I would like to see in terms of hardware, I would like to support like more the Texas Instrument hardware, like support for the programmable real-time unit, because I think that makes it more suitable for real-time products. And I would like a second port to something like an Allwinner CPU, because those are cheap and not well documented. That concludes my talk. I've not done most, let's say, the port was done in 2.5 years, 1.5 years, 2.5 years. And so many people worked on it. Ben Grass worked on it from 2005, has been part of the MINIX team. Linux joined just 1.5 years ago. Thomas Veerman did the frame buffer driver. Aaron Thomas did the initial work for the ARM port. And Thomas Cote was a Google Summer of Code student. Feel free to ask questions. Or not. Did everybody get it working? Yes?
How do you cope with driver latency if you put them into the user land?
Okay, sorry, can you repeat?
How do you cope with driver latency if you have a context switch back to user land, if you run your drivers in user land?
Right, so the question is, how do we cope with latency of the driver, because we have to switch back to user land?
The old 3.1 in NT often slow screen driver. Are you experiencing the same problem or similar problems?
It's hard to say. So the question is does context switching increase latency? Yes, it does. I think reliability comes at a cost. But we've seen on the x86 part, at least right now, that it's not a factor or two that makes it 2 times slower than Linux. So I think it is a non-issue right now.
Have you done measurements?
Have we done? Yes. Yes, in the back?
In your chart of all the embedded OSs on microcontrollers and ARM, so where do you position MINIX?
Yeah, I would like to put it somewhere on the map. The question is, where do you put Linux in there? At first, when I started, I expected to be in a part of where you have ARM MPU, because I mean MINIX is a bit smaller, it's more tweakable, you have more to tweak, and it's a smaller OS. So I would expect to have an entry in that area, but that area is really saturated with either On the left side, you have a library kind of operating system where you just include a bit of code there, and the commercial things. So MINIX, I'll see it still more on the ARM and supported with some hardware. So with FPGA or programmable real-time unit, I think is a nice place to be.
And yet you don't support any of the useful ARM features that would speed up the context switching like ASIC. So you have to use your TLBs on each fucking context switch. So do you have any plan to fix that? If you're targeting smaller amounts of CPU, you really have to do that.
It is very high on the wish list. But currently, there are no direct plans. As soon as we have time to do something at that area, we will do it. But currently, the work that's happening is on aligning with NetBSD to be able to integrate all the boring code, all the libraries, all programs, to be able to get those one running. Because if you have fast context switching but no applications, it's not such a good sales pitch either.
Well, if you don't have a system that actually performs, what's the point in adding features? I don't know, I would advocate for concentrating on getting something that is good enough and robust and fast before adding tons of features.
So the suggestion was to make it fast first, and I'll take that into account. Thank you. Yes?
Well, there are other microkernel-based operating systems, including open source ones. Wouldn't it be a good idea to combine efforts with them? Maybe exchange drivers in some of the user space, servers implementing different operating system functionality?
Right, so the question is, you're a microkernel-based operating system, why don't you go together with all the other microkernel-based operating system and get all together, get along, do your, there's a microkernel the room at FOSDEM, so people are talking together about that stuff. We research, we actually have implemented two things in the last 3 years. One was called DDE Kit, which comes from the Dresden University, which is an OS abstraction for things like threads, memory access, all the things that every driver needs. And a few drivers were written on that. So that's currently how we've got our USB support, is through those interfaces implemented. And then even using, for USB for support, we're using the Linux stack. It's still a lot of work. Currently our biggest chances of driver development are following RUMP, which is NetBSD's way of running kernel drivers in user space. And we're investigating that. But if you look at the chart, currently we're focusing on the BeagleBone Black, and we've got enough drivers for it to do something useful. USB is what we're working on because we want to be able to make a small NAS appliance or something like that. So we currently don't feel much need to do that. But it's a waste of effort to do that for everybody. Yes?
I use different targets at BeagleBone and I work on MINIX, right? So I have to remove some stuff you have done specifically for BeagleBone and add extra packages. So would you plan to extract this BeagleBone specific stuff from your code and pass it to more generic?
Yes, of course. So the question is, we're mainly focusing on TI hardware currently, and adding support for a different architecture poses problems because we're not there yet in terms of some make files or some drivers sometimes made assumptions on the OMAP. Being able to cope with that means either following the Linux approach of doing the device tree, following a device specific hardware and making your kernel cope with that, or look at NetBSD again for their way of configuring the kernel. And both of those require more work than we currently have. So currently we're waiting for the next platform to make it more generic. So come with your problems and we'll fix it. Any technical questions? Thank you very much.
Testing. Seems to work.
It might be a bit easier to actually hold it in your hand because it sometimes seems to have trouble picking up especially if it's too close under your chin. And then the problem is if you hang it on the side, like where you have a thing.
Yeah, we still have 5 minutes.
Yeah. You have time, don't worry. Because I think there's some people are going to shop and another dog head, so
Can you fix it to the...
Yes, of course.
Yeah, because they were placed too close and then you get all the...
This position should be okay.
Right?
Yeah. I used to do some audio before as well, so...
we have time. And I've seen quite a huge amount of your lasso around already.
Yeah.
Not even from our guys. Like the camera guy has one.
Nice. So we can be sure that the video will make it somehow if it's bad.
I asked him if he was happy with it and he said he was, so that's good. People are a bit hesitant. They're slowly coming in. Because the problem is since we have the K building, this kind of got isolated, so...
Yeah, exactly.
Yeah, Ines?
Sorry. I just wanted to say that I'm one of the guys who's going to talk for the XPCC framework.
Okay.
I just wanted to say that we're here. Yeah, we're here. He's not here right now, but he's going to be there.
Oh, good.
Good. Great. Tell me, does any of your slides cover the open source object common?
No.
You know what I told you?
Yes, I know, and I will be delighted to receive your questions.
I don't install apps, so I don't I'm wondering if you should ask how many people are you.
I do. No, I'm going to.
You're going to.
And that's very safe.
Gotcha.
Well, it's not 3 o'clock yet.
Still at Washington. Yeah, we're ahead of time still.
So I guess we can just give people a chance.
Yeah, we'll give people a chance to come here. I see Andrea has got pink. You have the wrong t-shirt, we should give you a pink one.
I've got a pink other arm.
Yeah. It's more purple.
Here. No.
We really have a pink one?
The other arm is pink.
Well, I know we have the purple one, but I didn't know we have the pink one.
The purple. Or maybe it was the first one.
So you have some swag to throw into the audience?
Yes.
Get some fights. It was my hat!
We have plenty of hats. There should not be no bloodshed.
Yeah. Well, you never know. We should try to win that and run.
Now this is it's forget I don't see it. It's not the machine within YouTube. No, I don't see it. It connects me.
Those are cool stuff. We get a free board to give away every year from Upload.
Oh, nice.
I don't know whose phone that is.
That's mine.
It's yours too, okay, because the guy who was sitting here earlier had also a white cover Jola.
It does a communication, so it says your
Damn you. hungry.
Where get
You want to throw them out for the first row?
Questions.
If the talks just stop now, it takes like 5 minutes at least.
Oh,
trying to take pictures of yourself?
It's a selfie.
Exactly what I meant.
Yeah, true.
Hello. See?
Yeah. Let's talk after the talk. I will.
Still people coming.
Oh, come on. I was taking a picture.
But yeah, you really have filled up the hour completely. Are you worried about that?
I think I'll be doing fine. I was in a heavy space. It took roughly 30 minutes to talk.
Yeah.
So, I'll be fine. I'm actually...
Like I said, there's still people coming in. We're in no hurry to start. Any new camera tuning or?
It's actually 2.5.
They just like to take pictures of themselves.
Next update, the battery will be better.
Okay.
Yeah. But I'm definitely sure I fixed your jumping and like weird value stick now. By battery, yeah.
By using the open.
Took me a while to port it in and then figure out all the details. But it works now. I even tested it. My parents looked a bit weird when I went to put the phone in the freezer and they're like,
I read that one.
what? Like my mom, what did you do in the freezer? Like, what the fuck are you doing? I just put my phone in there. My mom was like, what? Standard testing. Yeah. And my dad was like, my dad heard my mom and was like, you were doing what?
I think we're good now.
Yeah. I think we have a look. It's yourself, keep yourself. Give it a few seconds more. Yeah, don't worry. Yes, that's good. Just see if there's any questions. I don't know if you have any.
No, I'm not nervous. It's bored.
I think it's safe.
Yes.